Chapter 8, Non-Electrolyte Solutions, Section 8.5, Temperature Composition Phase Diagram. Let's look at a typical temperature mole fraction phase diagram of two components. We have component 1 and component 2. On the bottom, we have the mole fraction of component 1 from 0 to 100%. So over here, we have pure component 2. On the right hand side, we have pure component 1. This is a little redundant. We have the mole fraction of component 2 on top. It's a little redundant because x1 plus x2 is always 1. Now let's look at this 0.0 here. That means there's no component 1, there's 100% component 2. At this point, we have a low temperature, and component 2 is mostly in the liquid phase. There is a gas phase for component 2 even at low temperature, but usually the vapor pressure of component 2 is really low, lower than the standard pressure. And over here, this component 2 starts to boil. Alright, under the given pressure, it starts to boil. At this point, at this temperature, the liquid phase and the gas phase of component 2 are at equilibrium, and also the pressure of component 2 is equal to the external pressure. That's why you are starting to see the bubbles coming out of the liquid, only because the vapor pressure of component 2 is large enough to overcome the external pressure. And above this temperature, the vapor pressure of component 2 is going to be greater than the external pressure. And now mostly we'll just see the vapor of component 2, or just the gas phase. We have the same analysis for component 1. Over here, 1.0 is the mole fraction of component 1. Therefore, we have pure 1. And again, we can heat up liquid component 1 all the way up. We're starting to increase its vapor pressure. At this point, its vapor pressure is equal to the external pressure, and now we will be able to start to see the bubbles from the liquid component 1. Alright, above this temperature, the vapor pressure of component 1 is greater than the external pressure, and now we see just the gas phase on top. And not only we have 100% component 2, 100% component 1, we have some other mole fractions between 0 and 1. So over here you see two curving lines. One is dew point, one is bubble point curve. Now let's analyze the vapor of these two components. For example, right here, at this point we have really high temperature, and you can see at this point we have mole fraction of component 2 being 0.73. The mole fraction of component 1 is 0.27. Okay, again, 0.73 plus 0.27 is equal to 1. Alright, the two mole fractions should add up to 1. Now we start to lower the temperature. This is the temperature. We're going to lower the temperature. Nothing happens. But at this point, this is called the dew point curve. We're hitting the dew point curve. So at this point, we're going to see the condensation of the gas mixture. Alright, we're going to see condensation. We will start to see liquid being formed. And it's really interesting. You draw a horizontal line here. Alright, you draw a horizontal line here. So in the liquid phase, we actually have a different composition. So in the liquid phase, we have 0.38 component 1. We have 0.62 component 2. So what does that mean? That means actually there is a composition difference between the gas phase and the liquid phase. In the gas phase, we have again we have mole fraction of component 1 what is this, 0.27, and over here it's 0.38. So we can somehow enrich component 1 in the liquid phase. Alright, it goes from 0.27 in the gas phase to 0.38 in the liquid phase. And actually this is one way to purify one of the two components in a mixture in industry. Alright, it's usually pretty cheap to form the gas mixture and lower the temperature, and then we can somehow, in this case, enrich this component 1 in the liquid phase. And again, you can see there's two boiling point. The boiling point of component 1 is higher. That means it's easier to get more liquid 1. So that's the analysis. And we can further drop the temperature, but when we drop the temperature to here, the entire gas phase is converted to the liquid phase, and at this point, if we have all gas phase converted to the liquid phase, then the mole fraction of component 1 in the liquid phase is 0.27. okay, it's 0.27. So when you try to do this condensation to purify this component 1, make sure you just drop to this dew point curve and collect just a little bit of the liquid phase. In that small amount of liquid phase, we have a mole fraction of 0.38 for component 1. But if you keep lowering the temperature of the entire system, you won't be able to enrich component 1, because in the end, if you liquefy the whole thing, in the end the mole fraction stays the same. Now let's look at another vertical line. This time we will start from a low temperature. We'll look at this temperature lower than the boiling point of these two components, and we have a mixture in the liquid phase. We can keep heating up this liquid until we reach this point. This point is so-called a bubble point curve. That means right now we have the total vapor pressure above the solution being equal to the external pressure, and that's why you can see bubble being formed. Again, you have to have the vapor pressure being equal to the external pressure to start to see bubbles. Alright, now at this point we are looking at the formation of the gas phase. But again, the gas phase mole fraction can be different from the liquid phase mole fraction. If you look at the liquid phase mole fraction, you can see x1 is 0.38, x2 is 0.62. But when the gas phase is being formed at this point, actually the mole fraction of the gas phase, you draw a horizontal line, it's actually here. So you can see it's 0.73 for component 2 in the gas phase. So somehow, if you heat up the liquid mixture of boiling of component 1 and 2, and then you collect the gas phase, when you just hit the bubble point curve, you collect the gas phase in the gas phase, we have a 0.73 mole fraction of component 2, and this is how we enrich component 2, from 0.62 to 0.73. So it's doable. We can enrich component 2 by heating up the liquid mixture all the way to the bubble point curve, and at that point we collect the very small amount of the gas phase. In the gas phase, we have 0.73 as the mole fraction of component 2. It's definitely higher than 0.62. So by using this temperature mole fraction phase diagram of two components, we somehow can either enrich component 1 by doing the condensation of the gas mixture, or we can enrich component 2 by doing the vaporization of the liquid mixture. And again, we just need to look at the boiling point difference. Alright, over here, the boiling point of component 2 is lower, so it's easier to get more component 2 in the gas phase. The boiling point of component 1 is higher. Then that means it's easier to enrich component 1 in the liquid phase. Again, we have two components in this phase diagram, with component 1 with higher boiling point, component 2 with lower boiling point. And now we have some analysis, as I mentioned, at the dew point with Z1 equals 0.27, so 0.27 over here. There's the dew point, and at the dew point, the gas phase is at equilibrium with the liquid phase right here, and in the liquid phase we have x1 is equal to 0.38. 0.38 is greater than 0.27. That means we can enrich component 1 by condensing the gas mixture from here to here, and at this point we can collect the liquid phase at this temperature, and the mole fraction of component 1 is higher than that in the gas phase. And again, we can just also do this process backward. If we have the liquid phase of the mixture, we can heat it up, and then we can collect the gas phase at this temperature. And at this bubble point right here, we have a higher mole fraction of component 2 in the gas phase versus the liquid phase. So over here, again, it's just the analysis of enriching component 2 at the bubble point with Z1 equals 0.38. So that's this point. We have a liquid mixture with x1 equals 0.38, and it can be at equilibrium with the gas phase with y1 equals 0.27. So you can see, in the liquid phase we have higher mole fraction of component 1. In the gas phase we have a lower mole fraction of component 1. But if you look at component 2, we can actually enrich component 2 from 0.62 to 0.73. Alright, so again, when I draw this line, it actually indicates we have a gas phase here and a liquid phase here. They are at equilibrium. But how much gases, how much liquids are in the system in moles? Well, we can always use the lever rule to calculate the number of moles in the gas phase versus the number of moles of liquid phase. Again, we're looking at a two-component system, and we're looking at the temperature, mole fraction, phase diagram. But we're looking at something really weird over here. Over here, you can see at this point you have the dew point and the bubble point at the same temperature right here. So and this is actually higher than the boiling point of component A. It's also higher than the boiling point of component B. Alright, actually, since I labeled the axis as the mole fraction of A, so over here we have pure B, over here we have pure A. So somehow if you mix A and B with a certain ratio, for example right here, and then you can get a bubble point equals dew point, and this bubble point or dew point is higher than the boiling points of pure A and pure B. And when does this happen? Well, this happens when A and B attract each other more than they attract themselves. Here's one chemical example. When we have acetone and this trichloromethane, there's a very strong hydrogen bonding between the oxygen in acetone and the hydrogen in chloroform or trichloromethane. So really strong hydrogen bonding. So after we mix these two chemicals, the attraction between these two is actually greater than the attraction between two acetone. It's also greater than the attraction between two chloroform. So we have strong attraction between A and B in the liquid phase. That makes the boiling of the mixture more difficult. So at certain composition, the boiling point of this two the mixture of these two is higher than the boiling point of pure B and also than the boiling point of pure A. And since we have a higher boiling point than pure A and pure B, we call that maximum azeotrope. Okay, this is maximum azeotrope. We achieve the maximum boiling point. So again, it's just because A and B attract each other, they stabilize each other in the liquid phase, all right, more than what they can do to themselves. All right, so that's why it's really stable in the liquid phase. It's very difficult to convert the liquid phase to the gas phase. That's why you have a higher boiling point, all right, with the right composition. Now let's look at another example. I think we have over here water molecule. This is a water molecule, and this is the formic acid. So if you mix formic acid and water with the right composition, also you will see a higher boiling point than pure formic acid, and also higher than the boiling point of pure water. All right, and you can look up the boiling point of the pure substances and the maximum azeotrope in the appendix. There's appendix that tabulates some of the boiling points of acetone, chloroform, formic acid, water, and their mixtures. So you can see some numbers in the appendix. Just to emphasize, we have maximum azeotrope if these two pure liquids strongly attract each other, and these two strongly attract each other. And now, what if the attraction between A and B is lower than the attraction between A and A, and also lower than the attraction between B and B? Well, in this case, we expect to see a lower boiling point. All right, we expect to see the lower boiling point because the chemical environments of A in the mixture results in destabilization of A, so it's easy to evaporate A, and same for B. So when two components have lower attraction than the attraction in pure A and the attraction in pure B, we observe the minimum azeotrope. So it's called minimum azeotrope because the boiling point of the mixture is lower than the boiling point of B and also lower than the boiling point of A. A few examples: water and benzene. So between water and water, there's strong attraction called hydrogen bonding. Between benzene and benzene, there's also fairly strong attraction, but between water and benzene, there's not much attraction. Okay, between benzene and benzene, there's like dispersion, attractive dispersion. Between water and octane, and again you can see between octane and octane, there's fairly strong attraction between two octane molecules. Mostly it's dispersion. Between water and water, hydrogen bonding. Same here. Essential oils, those are really non-polar or low polar, and they attract each other via dispersion or attractive dispersion, and between water is hydrogen bonding. However, if you mix water and essential oil, there's a much smaller attraction between one water molecule and another molecule of essential oil. So that's why, because relatively when you mix these two, you destabilize both of them in the liquid phase. If you mix water and benzene, you destabilize water and benzene at the same time, and that means it's easier to convert the liquid phase to the gas phase. You have a lower boiling point for the mixture. Alright, so if you mix water and benzene with the right composition, you will have the bubble point and dew point with the same value, and that value is lower than the boiling point of water over here, and it's lower than the boiling point of benzene over here.